Hello everyone, I'm Zhiying Ye from Sensor product line, NOVOSENSE. Next, I will, together with my colleague Yuyun Yang, make a basic introduction of NSHT30. There are three parts of our presentation: a basic explanation of humidity and a description of how to use NSHT30 and how to run the demo board. Firstly, I will explain what humidity is. Humidity, as its name suggests, is actually a parameter indicating the content of water vapor in the air. Humidity can be described as absolute humidity parameters or relative humidity parameters. Absolute humidity parameters includes water vapor pressure. Absolute humidity, which means the mass of water vapor contained in 1 cubic meter of air. Also, there are some other absolute humidity parameters like mass concentration of water vapor and frost point, dew point temperature. Relative humidity is relative parameter to the absolute maximum amount of water vapor that the air can absorb at the moment. By the parameter of the maximum amount of water, relative humidity can be described as the conventional relative humidity, which means the proportion of vapor pressure of water. With the saturated water vapor pressure, the relative humidity can also be described as a difference in between water vapor pressure and the saturated vapor pressure, or the difference in dew point temperature. Humidity can be measured by a series of methods. For example, the traditional hair hygrometer. In this method, after absorbing water vapor, the hair will shrink to a certain extent, and the relative humidity can be determined by the shrinkage. In industry, thermostats typically are designed with a hygrometer using the wet and dry bulb method. The wet bulb will evaporate and experience a temperature drop, and the temperature difference between wet and dry bulb can be used to measure the relative humidity. Another relatively common high-precision measurement method is dew point meter. It controls the temperature of the mirror and uses the optical measurement method to identify the current critical temperature point of frost or dew, thereby judging the dew point or frost point temperature, and then determining the humidity. As researchers further deepen their efforts, some sensor products have come into being. In terms of size or easiness of signal processing, these sensors, relative to the previously mentioned methods, have great improvements, mainly further reduced in size and further improved integration level. As the development of MEMS technology, the processing circuit and the sensing element are integrated together to form a standard analog or digital output relative humidity and temperature sensor in a small package. NSHT30 is exactly an integrated temperature and humidity sensor based on the CMOS MEMS integrated technology. Its measurement principle is still capacitive. Well, what is capacitive measurement? In essence, the sensing material after the absorbing of water vapor will cause a change in its dielectric constant. By building a material-based capacitor, it is possible to measure the capacitance, thereby determining the changes in relative humidity. Since the capacitor is based on material, a variety of materials are available. For example, aluminum oxide, a common inorganic material. However, the reason why aluminum oxide is abandoned is that it has a relatively high temperature coefficient. In addition, its capacitance value changes in a non-linear way. As researchers deepen, attempts of using some organic materials such as polyimide and butyl acetate are used as sensing material. Polyimide now is widely used in temperature and humidity sensors. The reason is that in the CMOS technology, polyimide is a common material. Moreover, its linearity compared with other organic materials has a significant improvement. In life, relative humidity and temperature sensors have a wide range of applications. For example, refrigerators, washing machines, and air conditioners are equipped with relative humidity and temperature sensors. In industry, the applications include temperature and humidity measurement and monitoring in industrial sites. there are also some medical applications, for example, oxygen uptake channel, in which the sensors monitor the humidity inside the entire tube, helping improve the comfort of oxygen uptake. Automotive applications mainly include air intake manifold, in-vehicle air conditioner, and window auto defog unit. When it comes to NSHT30, functionally, it integrates temperature and humidity sensing from the perspective of functional block, a sensing unit comprising a temperature sensing element and a humidity sensing element, integrated front-end AFE, which performs amplification and linear processing of signals. Furthermore, it integrates a high-speed IIC communication interface, which outputs the measured data. Its operating voltage range is from 2 volts to 5.5 volts. Its package size is 2.5 by 2.5 millimeters, and 2 package forms are available, namely LGA and DFN. Next, my colleague Yu Yun Yang will present how to use NSHT30. Hello everyone, I'm Yu Yun Yang, an AE from sensor product line NOVOSENSE. Now I will look at the application perspective and explain how to measure temperature and humidity using NSHT30. Our temperature and humidity sensor NSHT30 provides 2 measurement modes, single mode and periodic mode. Single mode involves single trigger and measurement. When we need temperature and humidity data, send the address via I2C, write 0 × 88, and then send the single mode instruction. After receiving the instruction, the sensor will convert the temperature and humidity data, which takes 20 milliseconds, and send the read command via I2C and then read 6 bytes consecutively. At last, the host send NAC and stop to end the communication, and when measurement is done. The 6 bytes include 2 bytes of humidity data, 1 byte of humidity CRC, 2 bytes of temperature data, and 1 byte of temperature CRC. It's noted that CRC is used to verify whether the data communicated is correct. Therefore, after getting data, a check is typically carried out by performing CRC operation of the humidity and temperature data and comparing the results with the CRC data. After completion of the CRC check, the temperature and humidity calculation equation is used to convert the data to specific temperature and humidity value. Periodic mode refers to a periodic measurement mode. In this mode, send periodic mode instructions 0 × 27 and 0 × 37 via I2C, and the sensor will be always in the periodic measurement mode. At this time, the sensor will perform automatic measurement in a periodic way. When we need temperature and humidity data, just send Z000 to get the data at any time. After getting the data, we also need to carry out the CRC check and temperature and humidity data calculation. This is how the 2 measurement modes of NSHT30 work. In addition, it's noted that depending on the host you choose, there will be big endian and little endian problems. In view of this, when sending instructions and getting data, you need to pay attention to the byte order. In this part, I'll give some suggestions on the assembly of our temperature and humidity sensors. First, between the temperature and humidity sensor and the to be measured environment, there must be a physical contact channel, because the sensitive material of the temperature and humidity sensor needs to be exposed to the to be measured environment, and thus measurement can be performed. Second, the temperature and humidity sensor area should be physically isolated from what is inside the housing, so as to improve the response speed and reduce the effects of the air inside the housing on the relative humidity measurement value. Third, the space formed between the temperature and humidity sensor and the housing should be reduced in order to further improve the response time to the to be measured environment. Actually, this also can ensure that the sensitive material is exposed to the to be measured environment to the greatest extent, so as to avoid being affected by the internal environment. Last but not least, if the operating environment is harsh, for example, dust or water splash risks, a waterproof breathable membrane can be added at the opening of the housing to prevent the sensor from being contaminated or water egress. which otherwise may affect normal use of the sensor. Next, there are some suggestions on the layout of temperature and humidity sensor. To ensure that the sensor temperature is consistent with the temperature of the to be measured environment, improvements can be made in the following three aspects. First, the position of sensor should be as close as possible to the area to be measured. Heat source between the to be measured area and the sensor should be avoided to prevent the air in the to be measured area from being heated when passing through the heat source, which can result in inconsistency between the relative humidity in the sensor area and that in the to be measured area. Second, the thermal inertia in the sensor area should be reduced to improve the ability to follow changes in air temperature. The following methods can improve the ability to follow changes in air temperature. The first one is to reduce the PCB thickness by eliminating the need for bonding the middle thermal as far as possible or isolating the bonding pad from the PCB copper coating. The second method is the use of a separate small board which is connected to the main board via pins. The third one is to use an FPC board for connection to the main board. Third, the impact of temperature in other areas on the temperature in a sensor location should be reduced. Under the premise of mitigating temperature effects, the basic methods are as follows. The first one is during the assembly. Physical isolation should be formed between the temperature and humidity chip and the heat source on the main board, so as to reduce the impacts of heat conduction via air and heat radiation. The second method is to avoid direct sunlight exposure of the sensor as far as possible, in order to reduce the heat transfer via the thermal radiation path, which otherwise may lead to a temperature rise. The third one is that the sensor should be assembled on a separate subboard as far as possible. If the sensor must be installed on the main board, its position should be as far away from the heat source as possible. On the main board, holes should be created near the temperature and humidity sensor to reduce the impact of the heat source's heat conduction through the circuit board on the sensor's temperature. Next, I will show the demo board of our temperature and humidity sensor. The upper part is the MCU board based on STC design, and the lower part is the DUT board for our temperature and humidity sensor. Now, I'll demonstrate how to run a demo board for our temperature and humidity sensor. First, insert the USB for our temperature and humidity sensor's MCU into the PC's USB interface, and then open the executable file in the upper computer. Upon opening this file, we can see that the first window displays the temperature and humidity data. On the left is the graphical interface, and the right is the data display interface. At the top right corner shows the COM interface selected. In the second window, we can configure the temperature and humidity sensor. On the left is a single mode. For the single mode, there are 3 repetition rates to choose from: high, medium, and low. High repetition rate means that the conversation time will be longer, but the accuracy of data conversion will be the higher. Select high, medium, and low respectively. We can see that the instructions below will switch synchronously. That is, between the high, medium, and low instructions. On the right is the periodic mode, for which we can select the sampling rate. There are a total of 5 sampling rates, from 0.5 MPs to 10 MPs. 1 MPs represents 1 sampling per second, and 0.5 MPs means 1 sampling every 2 seconds. 10 MPs is the highest sampling rate, which means 10 sampling operations per second. Like in the single mode, the repetition rate can be set. With 3 repetition rates and 5 sampling rates, 15 instructions can be designed. After selecting a specific instruction, we can see a synchronous switch between the corresponding instructions. On the right is a setting area for reading all temperature and humidity registers. By clicking here, we can get data of the temperature and humidity sensor registers. Here shows the ID of our temperature and humidity sensor, and the user register is displayed below. Here for the alarm function of our temperature and humidity sensor, the temperature and humidity threshold can be set. In other words, when the temperature is higher than the threshold, and when the humidity exceeds the threshold, an alarm will be triggered. Below are the temperature and humidity values, to which the alarm will be cleared. Here are the specific values of temperature and humidity that can be converted to hexadecimal data, as well as hexadecimal data that can be converted to specific temperature and humidity values, indicating bidirectional conversion. Next, let's select the correct serial port, open it, and start tests. At this point, we can see that the software will display real-time temperature and humidity data. The upper computer can also save the temperature and humidity data. Click the Excel setting button and create a new Excel and name it DAT. Double-click DAT and check the Save button. At this point, the temperature and humidity data collected will be saved synchronously to the Excel file we just created. After the completion of reading, we can open the Excel and we can see column D and F, which shows the temperature data and humidity data of our temperature and humidity sensor. Column E and G also give the temperature and humidity data of our sensor. As our demo board can connect two sensors simultaneously, but in this case we connect one sensor only. Only the data of one sensor is displayed. That's the end of our presentation about the temperature and humidity sensor. For more information, please visit our official website.